everybody. Today I will speak about panspermia. I'm not an expert on the subject. I'm a philosopher of science. So I have a more modest goal to give you an overview of the different versions of the theory. So the first thing we can notice is that the Earth is very open to outer space. There are 500 to 300 tons of materials which arrive on Earth every day. So it's huge. It's a huge amount of things which come to Earth. Then I would like to go beyond the dichotomy of abiogenesis on Earth versus panspermia, but to entertain the possibility that both could be true, that life could have emerged here on Earth, but still there could be some transfer between planets or planetary systems. So the two problems are really different, separable: the problem of the origin of life and the problem of the distribution and diffusion of life in the solar system, in the galaxy, or even in the universe. So the worth of panspermia is that there are several points we can make. First, that for the origin of life, it could broaden the search space. As Francis Crick said, our Earth didn't need to have all the special conditions for life to start. So maybe if we don't manage to understand the origin of life on Earth, it's simply because the conditions were not here and life started elsewhere. But life could have emerged on Earth, but still receive some biological inputs from space, and life could still escape from Earth. Actually, it at least escapes with us humans doing some space exploration. And panspermia, even if it doesn't happen in the case of our solar system, it could still apply in other solar systems. We can't exclude that. So, if it were proven true, it could solve the origin of life on Earth, even though, of course, the original problem of the origin of life in general wouldn't be solved. It would just shift the problem. So what I'm interested in is a general biological worldview where we see the universe full of life instead of seeing just life here on Earth. So the outline of my talk will be a few words about the history of this idea. Then I will outline 8 key issues which allows to structure the different theories of panspermia. And then I will speak about the more controversial idea of, or speculative idea of directed panspermia, the idea that our life might have been seeded by advanced civilizations. Oh, sorry, I didn't mean to show you that. That's actually some argue that the prehistory of panspermia theories in ancient Egypt. I'm not sure about the interpretation, so I will go to the Nobel Prize story. So the father of panspermia theory is Svante Arrhenius. Generally, we consider him the father. He won a Nobel Prize not because of this idea, but of other ideas in chemistry. Francis Crick also developed the idea of directed panspermia. And other very notable scientists have explored this idea: Hermann von Helmholtz, Lord Kelvin, or Fred Hoyle. So to start with the 8 key issues, we can first start with the theory of lithopanspermia. So it means panspermia via rocks traveling from one donor planet to a recipient planet. So there are 3 main issues. First, life needs to escape from the donor planet. Then it needs to survive in space. And then it needs to arrive living in the planet B and develop and proliferate. So Nicholson, in a very nice paper, did summarize the probability of this to happen with the 3 stages here, and he goes in more details. So first, BIZ is the probability that the first rock impacts a biological zone. then that there are some rocks which are ejected, that the life which was in these rocks survives the launch outside the planet. Then it needs to survive in space, survive the entry in the new planet, survive the impact in the new planet. And then the probability that this life in the new planet is released. And finally, that it survives on the new planet and proliferates. So there are a lot of parameters. There could be other mechanisms of escape. For example, a flyby meteorite. So if you have planet Earth, a meteorite would just not hit the Earth, but just come very close and take some bacteria in the atmosphere, for example. Also, volcanic eruptions could be a mechanism, although I'm not sure what the status of this today. So the probability of surviving in space, the key issue here is the time it takes for life to be sterilized in space because of the harsh condition versus the transit time in space. So yes, if a bacteria is quickly sterilized by cosmic radiation, then it can't go very far. And some so this is controversial. Some studies say that it's highly probable that life can survive in space. Others say it's highly improbable. So there are a lot of arguments in both sides. So yeah, we saw that the probability of entering non-destructively on a planet depends on surviving entry, impact, release, and survival. Then there are, to give two examples in about Earth, there is a theory which is called neo-panspermia, and it's the idea that there are living things which come continuously on Earth. Of course, it's very controversial, but at least it's interesting because it's testable. The more things are claimed to come, the more we could take samples and try to test this. Then the even more controversial, what I call nudging panspermia of Fred Hoyle and Chandra Wickramasinghe, is the idea that not only there is continuous biological material which comes to Earth, but they actually contribute to make evolution progress or to change evolution on Earth. So it's a kind of wide idea. So what is diffused? We have seen during this conference that complex molecules, at least according to chemists, are in space. So this version of panspermia is kind of accepted, which is called molecular panspermia. Then there is a variation on this idea, which is called necropanspermia. And the idea is that even if life dies in space and it transits, then there are still the biological material of the dead living thing, which could then be used to make new organisms. Viruses also have interesting capacities. Some viruses are able to recompose themselves by, even if they are very much damaged by UV radiation, they infect a part of a virus which is damaged here, another which is damaged here. They infect the same cell, and they are able to reconstruct the whole genome of the virus. It's quite remarkable. Then it could be, there could be other microbes. Even in the stratosphere, Wainwright, he found a kind of titanium sphere, which is quite strange. I haven't, his paper is not cited at all. Well, there are some rebuttals, but there are really strange things in the atmosphere that remains to be analyzed. So what else could be diffused? Maybe some multicellular organisms, such as a very resistant tardigrades. Hoyle and Wickramasinghe also speculated about insects, that insects could transit in space. I don't think that anyone worked on this or really take this seriously. And another possibility which has been entertained is planetary ejection. So in a solar system where there are dynamic instabilities, a whole planet could be ejected. and therefore this planet could possibly feed life or impact other solar systems. So how are the entities diffused? There are two ways. We saw the direct ways with lithopanspermia, so via rocks. And the original idea of Aaron Huyss was what is called radiopanspermia. So it's the idea that cells could use the radiative pressure of the sun as a wind and travel like this. Now it is in disfavor because they couldn't travel naked for very long. But there could be indirect ways, and that's the general vision of Hoyle and Wickramasinghe, that you see on this diagram on the right, where there would be a whole cycle of biotic material which circulate in the dynamic of the galaxy. Another idea, also by Napier, is that life on our Earth could contaminate other solar systems. If there are big meteorites which hit the Earth, then some life might be ejected in the solar system. And then when the solar system moves in the galaxy, or when our other solar systems cross this zone, they could be in fact contaminated by Earth materials. So how far are the entities diffused? Generally, the theory is about interplanetary transfer, but it could be interstellar. Some say, some studies show that it's very unlikely, but with an indirect way it might be possible. Then there are some even more speculative intergalactic contaminations. I've learned here with a poster here that a galactic meteorite may have already fallen on the Earth. I'm not sure if it's true, but it sounds interesting. Or even more speculative, that some life could hop on the supernova ejecta and so travel very fast and far. And finally, on a universal scale, there are arguments which show that the basic chemistry of life is already ready 10 million years after the Big Bang. So that's extremely early, and at least it could make a possibility. What is the dynamics? The dynamics is very important for the general diffusion of life in the universe. It would determine the growth rate of life. What I call resilient panspermia is the idea that it's an idea which has been proposed where some life is around Earth in space because of a meteoritic impact, but then it's seeded again, so it stays in space and comes back. So it would be a kind of backup strategy for life. A recent model by Lin and Lube proposed that it has some implication for observing exoplanets with life because of the dynamics of how life would spread from solar system to solar system. So it would lead to clustering zones of habitable planets in the galaxy. There is this controversial paper also by Sharov and Gordon, which, by looking at the size of genomes, suggests that life started actually 9.7 billion years ago. I'm sure many of you would disagree. And now I would like to go to the more speculative directed panspermia. Here the interesting principle is what is called the principle of cosmic reversibility. It says that if we are capable of doing something in the future, then, given that there was some time available, another civilization might have done the same. So, in this case, there is a strong parallel with us willing to possibly do some space colonization and the idea of directed panspermia. So a limit case is what I call accidental panspermia, where an intelligent civilization would accidentally contaminate a planet. There is also a model here with a spacefaring civilization, which is a bit speculative. So for the main variables are different for directed panspermia. First, you need to have some advanced extraterrestrial civilizations. So it's the first variable here is a bit the result of the Drake equation. Then you need motivation to send some seeds, the technical capabilities to send, and also navigation capabilities. So what motivation? To seed or not to seed? That is a question I would like to ask you. Who think we should seed life in the galaxy? Okay. Who think we should not seed life in the galaxy? Okay.
Another question. Does it make sense at all?
Does it make sense at all?
You have to ask this question. Is it possible?
Of course, we do send things in space on Mars or.
Mars is not the galaxy.
Yeah, but it goes further on, don't they? I mean,
Yeah, okay, we'll talk about it later, but okay. So, well, I think the argument can be made that if there would be a major catastrophe on Earth, it would be a kind of backup strategy for life. It would be especially more important if we are really alone in the universe. Then, at least if we destroy Earth completely, there would be another life which could start somewhere. So what could we send? Biological entities, genetically modified entities, probes, etc. These are open questions. How to send? You might have heard the new project of Yuri Milner, who gave $100 million to go to Alpha Centauri and to send some small probes. And the idea to propulse them so far is to use a ground-based laser array, which would power enormous amount of energy so that they could go very quickly. So, and there is also the question of where an intelligent civilization would send, just in a random fashion, or would we target habitable planets? Or Motner argues that we should target star-forming clouds so that we wouldn't have any contamination issues of destroying other biospheres. So it's an ethical argument, actually. So now, if we think from the point of view of extraterrestrial intelligence, are they old enough to have done it already? The answer is yes. Some arguments show that, on average, they are 2 billion years or senior. So 2 billion years is a huge amount of time for technological progress, if you think about it. Targeting planets looks impossible due to the extremely precise navigation requirement to really go to a very particular place. If only there was a galactic GPS. Actually, there is. It's called XNav. And the idea is to use pulses which are extremely rapid and stable, and to trilateralize your position. And it really works like a GPS. And it's the amazing thing is that it's as precise. You can have 10-meter precision, even on the size of the galaxy. So often I read that directed panspermia is just an idea, it's not testable. I like to propose crazy ideas to test also. And so this is an image of a beetle where researchers discovered that they navigate by seeing the Milky Way and the starry sky. And they proved it by taking the beetles. They blindfolded them, and they put them in a planetarium, so they had a control condition, and they could demonstrate that these insects use the stars to navigate in their environment. So my idea is to do similar things with microorganisms we think could resist in space for a long time. to do this with the pulsar radiation, would they be able to steer themselves with pulsar radiation? We could do some controls, and also to go back with the original idea of aeronoise, could they also propulse themselves with radiation? So here it would be an example to use radiative pressure both as fuel and as a navigation system. So to conclude, I hope to have outlined some key issues that affect the spread of life. Of course, it helps more to appreciate our ignorance at this point, but as the Drake equation was very useful to structure debates, I think this kind of reflection could be useful to structure debates about panspermia. I mentioned many different kinds of panspermia, from lithopanspermia, neopanspermia, nudging panspermia, molecular panspermia, necropanspermia, radiopanspermia, resilient panspermia, superpanspermia, accidental panspermia, and directed panspermia. And yes, galactic navigation is relatively easy if you look at some pulsars. And I propose a test for directed panspermia. Thank you for your attention.